All right, this is page 519. 519, we did number 1 in the problem set real quick. Page 519 in the notes has an example problem that is like number 5. So 1 through 4 are identical problems. Well, not identical, but you use the same process. And then 5 kind of combines your knowledge and expands on this. So this is page 519 in your notes. Let me make sure I'm recording. Yeah. Okay. So yesterday we saw, I write it somewhat differently than your notes do. So if we are talking about, this is the enthalpy of a reaction. If we talk about finding the enthalpy of a reaction, given the enthalpies of formation, what you're going to do is sigma. We are used to that in physics. That means sum of. So you're going to take the stoichiometric coefficients, that's the n, and then multiply by the enthalpy of formations of the products for each product. And then you're going to subtract the same thing, the sum of the stoichiometric coefficient times the heat of formations of the reactants, each reactant. So that gives you delta H of reaction, and delta H of reaction is in joules or kilojoules, kilojoules per mole of reaction. So what that means is that for every 1 mole of reaction, we need this many kilojoules. So basically that means for every reaction, if we have the perfect stoichiometric coefficients, we need that many joules. So this is just an expansion on yesterday. We did number 1. How did that treat you? Did you understand it? I know I went quickly, but. Okay. So we're going to see a problem like number 5 on the problem set. On page 519, the examples number 1 is just enthalpy stoichiometry. So that is like 6 through 8. Okay, it's just stoichiometry. So let's do number 2. 4 NH3 plus 5 O2 yields 4 NO plus 6 H2O. So the given in Appendix L I'm just going to do this to save some time, save some writing. Delta HF of N H3 is negative 45.90 kilojoules. Delta HF of NO is 90.29 kilojoules. And delta HF of H2O is negative 241.83 kilojoules. All right, so we want the enthalpy of reaction first. The full problem is using the information in Appendix L. Calculate the quantity of heat evolved or absorbed in the oxidation of 10.0 grams of NH3. So first step, we need to find delta H of the reaction. And remember, that the units are kilojoules per mole of reaction. So this is nothing but delta H reaction is N times delta H product minus the sum of N times delta HF, the enthalpy of formation of the reactants. Therefore, delta H of this reaction is going to be 4 times delta HF of NO plus 6 times the delta HF of H2O minus 5 times delta HF of O2 plus 4 of 4 times delta HF of NH3. Now, the reason why we have 4 times the delta HF of the NO is because we have 4 moles in the reaction. Okay, 6 times delta H2O because we have 6 moles in the reaction. Again, 5 moles times the delta H of oxygen, O2, because we have 5 moles of O2, plus 4 moles of the delta HF of NH3 because we have 4 moles of NH3. Now, one of these delta HFs are 0. Which one is it?
Is it going to be the end of the two that end up equaling each other?
Nope. I said it in passing, but the enthalpy of formation of elements is 0. So which one's your element? It's capital N, capital O.
Yeah.
So that's compound.
Oh, element, right.
Yeah, element. So the O2. So the 5 times delta HF of O2 is 0. So this becomes delta H of the reaction is going to equal 4 times 90.29 plus 6 times negative 241 minus 5 times 0, which is 0, plus 4 times negative 45.9. Put parentheses around the first term, the first sum, and then subtract, and then put parentheses around the second sum, and you'll get it. And you get negative 906.22 kilojoules per mole of reaction. So that's real simple. That's how you do 5A. But 5B in the problem set says that, let me read the problem. Five B says calculate the heat produced from 1 gram of butane. And in this problem, we want the enthalpy of evolved or absorbed by 10 grams of NH3. So do we have perfect, is this a perfect stoichiometric amount of NH3? No, it's not, because 1 mole of NH3 is 17 grams. And we've got 4 moles of NH3. So we would need 4 times 17 to be a perfect stoichiometric amount, right? So we have to do stoichiometry after this. And I'll show you how that works out too, because it's a little funky using this mole of reaction. Okay, but notice that the moles is not moles of each thing. It's moles of reaction, the whole thing. It's worth asking, is heat evolved or absorbed in this reaction? Very good, it's evolved because it's negative. We have an exothermic reaction. The reason why it's negative is because the sum of the products is much greater than the sum of the reactants, because you have the negative term for the enthalpy of formation of H2O. And if you didn't get this down, I can copy my notes. All right, so now stoichiometry. Wait, no, stoich. Okay, so we've got 10.0 grams of NH3. What do we have to calculate first? Moles, yeah. We have to go moles. So let's use the exact amount, 17.04 grams of NH3 per 1 mole of NH3. Now, that's not where we stop. We have to use this per mole of reaction. So for 1 mole, which means just one reaction, how many moles of NH3 do we need for a perfect reaction? We need 4, just your stoichiometric coefficient. This is kind of a mole ratio, but it's per mole of reaction. So you have 4 moles of NH3. And that's going to be 0.1467 moles of reaction. That's how many moles that of the reaction that actually take place. So now you're going to do some stoichiometry with your delta H. Oops, that's third. Can't count. Your moles of reaction is going to be your given. We want moles of reaction to cancel out. And we are asked for kilojoules. I'm going to have you recall that for every mole of reaction, there is negative 906.22 kilojoules. So what goes with kilojoules? A negative 906.22 kilojoules. That's going to cancel out my moles of reaction and give me kilojoules like we want. And delta H is going to be 132, negative 132.95 kilojoules. So negative 133 kilojoules. Questions over that? All right, great. We now know how to do 1 through 5, and then the next section, 6 through 8. And we know how to do 10 and 11. We do not know how to do 9 yet. 9 is tomorrow's lecture. Okay, I know I promised a work day, but I want to get through this lecture. We have 2 more lectures to get through, a lab, and then we'll call it a day on this chapter. Now, I will say that the next few chapters are going to go insanely quick. Because I'm going to assume that people have some background knowledge from either chemistry or physical science or both. Okay, so I'm not going to spend a lot of time on these next sections because I want to get to reaction kinetics and equilibrium. So, I mean, the next sections are electrons, periodic table, bonding, intermolecular forces, molecular orbital theories, things that I can rush through or have you read through. So just know that that's coming. All right. So you can have the rest of class.